It's morning in the cloud forests of Ethiopia. The sun rises in the sky, the white mist burns away, and we see a spindly coffee tree. And today, it's a big day for this coffee tree because one of its little babies is setting off on a big adventure. On the end of one of her long branches hangs one of her babies, a little red coffee cherry. Now, the baby isn't the red coffee cherry itself. It's not even the green bean inside. It's the tiny little embryo in the middle of the green bean. And the embryo, it's literally a little tiny coffee plant, shaped kind of like a white shovel. Its spade-like top is going to grow into a couple of leaves, while its trunk will grow down into a root. And today, it's going to embark on a long voyage. The biggest voyage of its life. The only voyage of its life. An animal is going to eat it. And right on cue, a bird swoops in and lands on a nearby branch. It turns its head sideways and its piercing eyes lock on to that red, juicy coffee cherry, where, deep inside, sits our little spade-like coffee embryo. It swoops in, plucks the cherry off the tree, gulps it down, and then flies away into the distance. The green seed makes its way through the internal organs of this bird, and a little bit later on, it's plopped out the back of the bird. It whizzes through the air and hits the ground. The green coffee seed lies on the floor alone in the middle of an Ethiopian forest. Huge trees tower overhead, while hordes of ants with sharp jaws scutter all around. But everything is going to be fine. Because its mother was a very caring parent. She's packed this big green rucksack for her little baby's big trip. And in this green rucksack, there are lunch boxes full of food. And so it grows a little white root that buries its way into the soil. And the mother plant has also packed away in that green rucksack some cans of insect repellent in the form of caffeine and chlorogenic acids that put off the bugs that are crawling all along the forest floor. The baby eats, and right at the moment where it's finished all the lunch boxes of food, licked them all clean, two little leaves fly open. And it's ready to catch the sun's rays and feed itself. At the same time, on the other side of the world, in Brazil, another coffee tree has done the same thing and got ready for a bird to come along and take its baby away on a big trip. But instead, a giant machine comes roaring down the mountain. Vibrating rods whack the mother so hard and fast, the cherry flies off the branch. It gets hurled into the back of a truck, driven away, dumped out, squeezed between giant rolling mills. The red juicy flesh is stripped away. Then it's thrown across a hot concrete patio, baking under the tropical sun. It's tied up in a dark bag, floats on a metal ship. The seed moves halfway across the world and then gets thrown into a burning hot spinning oven. The coffee seed, now roasted, is crushed in a grinder. Hot water dissolves a lot of the nutrients the mother plant put in that green backpack for the embryo to eat. And some random shaved ape that walks on two legs and yaps into a microphone for a living puts a cup of that liquid to its lips and takes a sip. It's good coffee. The world is a very strange place. I kind of wonder, what if we could interview a coffee plant and ask it, so how do you feel about the fact that that food you packed away for your little baby to eat, it tastes really, really good when we roast it up and dissolve it with water. But this is what's happening. Baby plant food is getting transformed during the roasting process into coffee flavors. Conceptually for me, that is a crazy thing. And that is why I made this episode. I wanted to understand, how on earth does baby plant food get transformed into delicious coffee flavors? And so, in this episode, what I'm going to show you is how 2 nutrients that a mother plant gave its embryo to eat, how they help the coffee embryo grow when it's out in the wild, and how roasting transforms them into aromas we love in our coffees. And I'm not going to tell you what they are just yet, but these are aromas that are created in the Maillard reaction, one of the most important flavor reactions taking place during coffee roasting. The reaction we're going to pull apart step by step. And my partner sponsor for this episode is Probat, who I chose to work with because they are the world's largest manufacturer of roasters and also one of the world's oldest, with teams of over 50 people dedicated to the science and engineering of roasting. So strap in, because things are gonna get weird, microscopic, and delicious. I'm James Harper, and this is Filter Stories, the untold stories hidden in your cup of coffee. And this is my 3rd series on the science of coffee, a journey into coffee's hidden microscopic secrets. So, we're back in the cloud forests of Ethiopia. The tiny seed has fallen out the back end of a bird, and it's now nice and snug, buried in some warm soil. And what we're going to see here in this first half of the episode is how 2 nutrients in the green seed, sugars and amino acids, how they help this little tiny seed grow into a coffee plant. A few days later, the skies above darken. Rain falls through the forest, and it drips into the soil all around the coffee seed. The seed absorbs this water, and it begins to germinate, as in, it begins to grow. So remember that green backpack of food that the mother plant gave its baby for its big trip? Now, that backpack, what it actually is the green bean itself, where deep inside is the embryo. The embryo is cocooned by green bean. Now, we're going to focus on just 2 of the nutrients contained in this backpack full of food: amino acids and sugars. Both amino acids and sugars are going to help this little baby embryo grow a little root and 2 little leaves to catch the sunlight. All right, guys, now I have to confess something here. Back in school, I was awful at biology. I just could never wrap my head around it. But for this episode, for the first time since I left school, I went deep into plant biology. And I've got to say, as an adult, it was so fun to discover that how plants work biologically, a lot of it explains how you work biologically. I couldn't believe how much we human beings have in common with plants. So let's get into it, and let's look first at amino acids. All right, so amino acids, they are just tiny microscopic compounds that look like those molecules you'd build back in chemistry class back in school. You know, you stick the balls and sticks together to kind of create these shapes. That's basically what an amino acid is, one of those things. And if you squint really hard, it kind of looks like an ant. Now, a single amino acid by itself, it ain't doing much for our green coffee seed. But when it combines together with other amino acids, okay, now it's actually doing something helpful. Because those amino acids come together to form proteins, and some proteins function as enzymes. And now when you hear the word enzyme, I don't know what comes to your mind, but I'm like, yeah, I've heard of an enzyme, but I really have no idea what it does. Enzymes are like these little biological machines. Without enzymes, you'd be dead. And without enzymes, this coffee seed ain't going to grow. It's really so foundational. And for example, in your body, the alcohol in your liver is broken down by enzymes. In the saliva in your mouth, when you chew on bread for a while, it just magically starts to taste sweet because the starch in the bread is being converted to sugars by enzymes. And what enzymes are like these long strands of amino acids, all connected together like a long line of ants. And these enzymes can get super long. Like we're talking 300 amino acids all strung together. And if an amino acid looks like an ant, like picture 300 ants like all connected together in a long chain. Some enzymes are over 1,000 amino acids long, like 1,000 amino acids, like ants, all connected together on this extremely long strand. And depending on how long these enzymes are, they do different things. Like, for example, that enzyme in your mouth that breaks down starch, that has 500 amino acids all connected together. But one of the enzymes in your liver that breaks down alcohol, it's only 400 amino acids long. Okay, so that's us humans. But what about seeds? Coffee seeds. Now, in seeds, enzymes do a kajillion things. Duplicating, cutting, converting, catalyzing. And just to give one example, enzymes help the embryo cells duplicate, right? Like the embryo, that little white shovel mini baby coffee plant, it grows into a big plant by just duplicating itself. Every cell in the embryo duplicates itself over and over and over again. And that's how embryos grow into little coffee seedlings. That's how you grew when you were in your mother's womb. You, once upon a time, were an embryo. Your cells duplicated themselves over and over and over again until you became a baby. And it's the same thing with plants. Human babies, plant babies, all embryos grow by duplicating their cells. And enzymes are critical in that process. For example, one enzyme, which is like over 1,000 amino acids long, it comes along and builds a cell wall just before the cell is about to split. And then a different enzyme comes along, this time only 800 amino acids long. And this one cuts the cell in two. So now the cell has duplicated. And so as the embryo grows bigger, as its cells duplicate over and over and over again, eventually a little root buries its way deep into the soil. And two little leaves fly open, ready to catch energy from the sun. So that's the first thing, amino acids. Amino acids, they come together, they form these long chains of enzymes, and enzymes do a kajillion things to help little embryos grow. And so now let's turn to the second nutrient, sugar. Okay, so this little baby embryo, it needs energy to power everything. Now, as we know, plants get energy from sunlight. But to be able to catch sunlight, you need some leaves. But this coffee seed doesn't have leaves. It's just a green seed. And it needs energy to even be able to grow leaves in the first place. And it gets that energy from sugar. For you biology nerds, this is glycolysis. So the mother plant in that backpack, she packed away lots of little lunchboxes full of sugar. But to actually get the energy from the sugar, what happens are enzymes, again, different enzymes, they come along and they act like a little pair of scissors that cut up the sugar. And every time sugar is cut up into smaller pieces, energy is released. And while this energy is being released, there are these little batteries that charge up from this energy. These little battery molecules, they're called ATP, adenosine triphosphate. And it's this energy from these little ATP batteries that give a plant life, fuel to just power the cells, keep cells running. It's like every cell in your body is a bit like a smartphone. It has a battery, and when the batteries run dry, the cells die. And by the way, you are full of ATP as well. Like, that's how we run. In every cell in your body, there are these ATP batteries that keep your cells alive and running. And so that's what sugars and amino acids do. Amino acids, they come together, form these long chains of enzymes. And enzymes do lots of things that just help the baby plant grow, from building cell walls to then cutting those cell walls to duplicate cells. And then there's also sugar. When enzymes cut sugar, it releases this energy that's stored by ATP batteries. And these ATP batteries power all the cells in the baby plant seed. Now, also, really importantly, I don't want you walking away from this episode thinking that this is the whole story. I have simplified so much. Sugars and amino acids do many other things, and there are many more nutrients than just sugars and amino acids in a plant seed, all helping a baby plant grow. But hey, we're trying to simplify things here. And so we've seen how a mother plant packs away sugars and amino acids for its little baby to grow. And here's the thing. If you were to taste a green bean by itself right now, like brew it like you would a regular coffee, those sugars and amino acids taste nothing like coffee. And I know this because I did this in the previous series. I ground up some green coffee, brewed it like a regular pour over filter coffee, and it kind of tasted like green grass, slightly sweet, nothing like coffee. And if you want to hear my reactions to tasting green coffee, I have that episode linked in the show notes. But everything changes once you roast the coffee bean. When it gets really hot, the sugars and amino acids go on a very long chain of reactions, which at one point you can get delicious aromas. Aromas that make us come back to coffee over and over again. And this is what we're going to explore next. We are hopping into a spacecraft, shrinking ourselves down microscopically, and we're going to see the Maillard reaction up close. So on a dark, cold autumn day, I took a train from my home in Berlin to West Germany, near to the border with the Netherlands, a little town called Emmerich am Rhein. And I went to visit Probat, manufacturers of coffee roasters. And coffee roasting is the place where baby plant food transforms into delicious flavors. Now remember, sugars and amino acids, they don't really smell of anything. But during roasting, they are responsible for some amazing aromas we love in our coffees. And I was like, how does that actually work? What is going on microscopically? What even is flavor microscopically? This is what we're going to see. It is a weird, fascinating place.
Great. Sure. Okay. So we can start the roaster if you want to.
Yes.
Fan and drum.
The button turned green.
So I'm in Probat's cupping quality control room with Ilvana Weiler.
I am a trainer and consultant here at Probat.
And Ilvana has just fired up the 1 kilo roaster sitting in the corner of the room. And sitting on the floor is a big green bucket full of green beans. And now what we're going to do is shrink ourselves microscopically to go inside one of those beans. Ah, right on time. Our spacecraft. Here, hop in. Strapped in? Good. We're off. We're shrinking down and flying towards one of those green beans in that bucket. And as we get close to it, it grows to the size of a planet. As the bean gets bigger, we can now see the cells that make up the green bean. Hundreds of thousands of cells stretching all the way into the distance, curving over the horizon. And it just kind of looks like honeycomb. All these cells are different sizes, some are bigger, some are smaller, all squished up against each other, divided by thick, strong walls. And although we can't see it, deep inside that bean somewhere sits a little shovel-like coffee embryo. Now, what we're going to do is zoom into one of those honeycomb cells, because it's in each and every one of these cells, reactions are going to take place that give us coffee's beautiful flavors. It's quite a sight. One of these little honeycomb cells, it is half the width of the hair of your head. It's that small. But right now, it's the size of a city. It's like when you're flying into an airport and you can see an entire city out the window. That city is one green bean plant cell. Surrounding the city, we see mountains. Huge, tall, towering mountains wrapping all the way around this city. These are the cell's walls. Here's the coffee scientist Sebastian Opitz from the Coffee Excellence Center in Zurich, who helped explain all this stuff to me.
You have the cell walls around, so this is a very hard and rigid structure, and it's very thick.
And next to these high mountains, we see the cell's nucleus.
Brain of each cell would be the nucleus.
And the nucleus is like a castle that governs the city all around. All the streets and suburbs moving outwards from the castle. And then we find a lake. Technically, a vacuole.
That is a water-rich repository.
This giant lake is like the cell's storage room.
Everything that is not needed otherwise, because it would disturb the finely regulated processes for running the cells, this is all kind of the storage room.
And this lake is much smaller than it used to be. When the coffee seed first fell off the branch, this was a huge lake. But it's been dried out over time. But still, it's a lake. And so, out the window, what we see is a beautiful city, a castle, what used to be a giant lake, all surrounded by towering mountains. And all the coffee flavors that we love, the basic components of them are right here in front of us. There are sugars, proteins, chlorogenic acids, lipids, caffeine, everything that produces coffee flavor is inside this cell. They might be hanging out in the lake. They might be on the walls of the cell in the mountains. They might be in the nucleus in the castle. Point is, many of the world's leading coffee researchers hypothesize it's in these cells, when we apply heat, chemical reactions take place that give us gorgeous coffee flavors. It's like each cell in its own right is its own mini roasting chamber, or as Sebastian Opitz put it,
Like a microreactor.
a microreactor. So when we heat up the bean, all this stuff is going to react in lots of crazy complicated ways. There are going to be explosions, transformations. It's going to get so messy. But at one point, delicious flavors are going to be created. What we're about to see is the Maillard reaction. This is a reaction that you control all the time when you're in the kitchen. When you're frying onions, hey, that's a Maillard reaction. When you're toasting bread, hey, that's the Maillard reaction. And it is one of the most important reactions in coffee roasting. And to be clear, there are so many different types of reactions in coffee roasting. Maillard is just one of them. But my goal for this episode is to help you conceptualize what's really happening microscopically when we roast coffee. And so we're going to follow just one type of flavor reaction. Reactions that will involve sugars and amino acids, the two nutrients we saw in the first half. And it's a 5-step process. And what are we waiting for? Let's go. Step 1, getting this water super hot.
Not all the coffee we roast here is thrown away. Some of them.
Out the back window of the spacecraft, we see a ginormous Ilvana. She grabs a scoop, plunges it into our bucket, scoops us up into the air, and then dumps us into the top of a roasting drum. We fall through a metal chute, and we're now in the belly of a roaster. Whew, it's getting hot in here, guys. I'm activate the cooling mechanism so we can stay safe. Much better. All right, now I want to show you the best action. So let's dive into that lake. Now, we can see a lot of random stuff floating around in this lake, but strain your eyes to look just at the sugar. There are these strands of sucrose bobbing around. And again, it kind of looks like just a chemical molecule, the same sorts of ones you put together back in school with like balls and sticks. But if you put a gun to my head and force me to describe it, sugar looks like spiky rungs of barbed wire stuck together. And I really want to give you a sense of scale. This piece of sugar is as small as a human in a big city. And the city, of course, being this green bean cell with its castle and lake and towering mountains all around, which is itself half the width of a single hair from your head. All right, so we're now a minute into the roast, and it's getting really hot. And what we're seeing is that the water in this lake, the H2O molecules, they're moving faster and faster. Back at room temperature, they were really just chill, just sloshing around here or there. But with all this heat, this energy, we've gone from a very placid lake to some really stormy, rough seas. This water is actually above 100 degrees, like it's above the boiling point. But most of it isn't boiling at all because the strong cell walls are keeping the water from evaporating, like a pressure cooker. And so deep in this water, the currents are just going crazy. And in these currents sits our sugar molecule, those spiky rungs of barbed wire, being pulled this way, that way. And now we see hydrolysis. We see the water cutting the sugar in two. As this long strand of sugar is pushed this way and that way in the currents, protons and water come together to smash it in two. Before we had a long chain of simple sugars stuck together, but after this reaction with water and protons, we now have two simpler pieces of sugar floating around. And now these simple sugars, fructose and glucose, are going to react themselves. We've arrived at step 2. So out the window of our spacecraft, we see these two simple sugars, and they kind of look like wedding rings.
Cyclic form, like a ring structure.
This is Anya Ran, another coffee researcher who was so helpful in helping me wrap my head around this complex chemistry. And Anya is an expert on this chemical process we're looking at here, the Maillard reaction, and is about to come up with a book on the topic as well. Link in the show notes. So we had a long chain of sugar, and then water and protons came along, smashed that long chain of sugar into simpler sugars, and now these simpler sugars, their atoms are all arranged in the shape of a ring. And in this water here, they're just bouncing around. And there's lots of stuff to bounce off of. Lots of different other molecules. But because this small, simple sugar is in this ring form, nothing happens. It just bounces off random stuff and floats off in the opposite direction. But the temperature inside this roaster is still climbing. We're well past 100 degrees now. It's getting really, really hot. And what we start seeing is these rings of fructose sugar, they snap open.
Sugars can actually open up into a straight chain.
And the sugar molecule, it's gone from a ring shape to a centipede-looking thing. Like, nothing's changed in terms of the number of atoms. Just what's changed is their shape, how they're arranged. They've gone from a ring to a centipede. And this now brings us to step 3. Sugars react with amino acids to produce glycosylamine. So we had water, we heated up the water, it then broke these complex sugars into simpler sugars, and then these simpler sugars, which were in ring forms, they snapped open. And now they're in the form of a centipede.
And it's only that form that's actually reactive.
And this centipede is raring to react. It is dying to smash into something else and change. And there is something nearby it will react with. Guys, this is now coffee roasting safari. Out the window, we see two creatures. On the left is our simple sugar centipede. And then on the right, we see an amino acid. And remember, amino acids, we've seen these before. They kind of look like ants. And like we saw in the first half, when a baby plant embryo is growing, amino acids come together to form long chains of enzymes. But right now, we're just seeing one amino acid by itself. Now, there's something pulling together this centipede sugar molecule and this amino acid ant-looking thing. They're headed on a collision course. One of them has too many electrons, whereas the other has not enough. And because of that, they're like attracted to each other. They come together and bam! Chemical reaction.
So this is called then N-substituted glucosylamine.
And this new molecule is a fusing of the sugar and the amino acid. And what we see in front of us now is a truly awful sight. A total Frankenstein creature. Some kind of ant centipede hybrid. This is glycosylamine. For you chemistry nerds out there, a type of Schiff base. Guys, and this monstrous creature is getting a bit close, so I'm just going to reverse the spacecraft for a second. So guys, just to remind you, this monster in front of us, this ant centipede sugar amino acid thing, it's actually made up of two pieces of baby plant food. Two pieces of food that the mother plant gave its little embryo to eat. The amino acids would come together to form these long chains of enzymes that cut and duplicate the embryo. And when the sugar gets broken down, it produces ATP energy. But because we've applied so much heat, we are now in the middle of the Maillard reaction. And what we've done here is just reacted these two pieces of baby plant food together. And it's produced this weird glycosylamine Frankenstein molecule. And if we were right now to stop the roast, dump out the beans, and brew up this roasted coffee, it still wouldn't have much of an aroma. We are still not at a stage where we are going to get really amazing flavors. But we're very, very close. Coming up, step 4. The monster transforms. All right, guys, so we're now about 7 minutes into the roast. We've passed 150 degrees Celsius. It's getting really, really hot. And I know, up until now, we have seen a lot of change already. Let's quickly recap it. We flew into the city to see a castle, a lake, towering mountains all around. And then as the bean got hotter and hotter, the water molecules started moving around super fast. They slammed into the sugars and broke them into smaller pieces. We saw those simple sugars go from ring forms into very reactive open shapes. And then they reacted with amino acids to create glycosylamine, this centipede ant monster Frankenstein. But it itself doesn't smell of much. No, there need to be even more reactions before we get an aroma we love in our coffee. Here we are, part 4. Glycosylamine transforms. The bean is getting hotter and hotter. And all this extra energy makes our glycosylamine monstrous ant centipede thing rearrange itself into a new structure. Like a transformer going from a robot man to like a car. And as the heat keeps building up, we see entire limbs of this new creature just flying off. Cue dramatic sci-fi sound. Then it also fragments, splits into different chunks. Ooh, that was a good one.
And then we produce something that is called decatones.
After that awful creature rearranges itself, we have decatones. And this new creature that's formed, it's much more sleek. compact compared to that Frankenstein thing earlier. And hey, let's just say it looks like a beetle. Yeah, that's what an alien beetle would sound like. And the amazing thing about this beetle is that it has two big glowing eyes. Its eyes are the decatones, parts of the structure that are inherently reactive, and what they react with is going to create, in the next step, coffee flavors that we love. And that brings us to step 5. Guys, we are now past 200 degrees. First crack has taken place, and we are in the key flavor transformation stage. What this beetle reacts with next is going to finally create coffee aromas. And it is going to react with amino acids. The same simple compounds we've seen before so many times. The little ant scurrying things.
And they produce, for instance, then these very powerful flavor compounds.
And depending which amino acid this beetle reacts with, we get different aromas. And for the chemistry nerds out there, this is Strecker degradation. For example,
3-methylbutanol is produced from leucine.
now remember how amino acids here look like ants? So out the right window of the spacecraft, we see a particular type of amino acid scurrying around like an ant. The beetle with the glowing decatone eyes sees the ant and it charges towards it. Its big glowing decatone eyes lock onto the amino acid and boom. We have 3-methylbutanol. And it looks like, oh God, how do you describe this? Again, balls and sticks and whatever, but kind of looks like a scorpion. Big, powerful tail that can whack the ground. And this scorpion-looking molecule, guys, this is it. We have got it. This is a delicious coffee aroma. Here it is, 3-methylbutanol. Oh, you don't recognize what that is? Aha, well, it makes our coffees smell a little bit malty. A lovely aroma, like fresh malty bread straight out of the oven. And in small amounts, this malty flavor can add depth, complexity to a coffee's aroma. You know, it might serve as a nice counterweight to very bright fruity flavors. And guys, here's one of the strangest things about this whole story for me. Here we have this scorpion-looking molecule, 3-methylbutanol, which gives us a malty aroma. Now, if you compare the shape of this molecule, with the sticks and balls, to that other molecule we saw earlier, that ant, centipede, Frankenstein, glycosylamine, why does this scorpion-looking molecule give us an aroma, yet the ant, centipede, Frankenstein, glycosylamine doesn't? From my perspective, they are very similar, just balls and sticks. All aromas at the end of the day are just balls and sticks, tiny little molecules. It just happens that some of these microscopic compounds give us smells, and others, which could look extremely similar, don't. Like, why? Why doesn't every microscopic compound give us an aroma? And in an earlier draft of the episode, I explored this weirdness with insights from Paul Breslin of the Monell Chemical Senses Center. I took it out because it was kind of derailing the story, but I'm going to create an infographic on Instagram which explores this further and hopefully might even make you question your very existence. What reality are we even in? Alright guys, so right now we've passed first crack and flavors are changing dramatically. Out the window of our spacecraft, we just saw a scorpion being created, 3-methylbutanol, a compound that gives us a malty aroma. But at this stage in the roast, it's just one of many different aroma molecules that have all just been created all around us from different reactions. For example, that beetle with the decatone eyes, it could charge into different amino acids to create very different other compounds, some of which might maybe smell floral to us.
For instance, a phenylacetaldehyde is being produced from phenylalanine.
And that's just within the Maillard reaction. There have been so many other reactions going on all around us that we haven't even paid attention to, but they too will create aromas. And also, there are some aromas that actually don't change at all during the roast. They're like in the green bean, and they just make it into our cups of coffee, unchanged by all this roasting madness.
Fruity esters are produced during fermentation. These are present in the green coffee, and then they are surviving the roast process, and then they are also relevant in the roasted coffee.
All right, guys, but right now, it is over 200 degrees Celsius in this roasting drum. It is so hot. Things are reacting so fast. Ilvana Weiler, if she wants these flavors right here, she has to stop the roast right now. Otherwise, these flavor molecules are going to react again and create new creatures which may give us aromas we don't like in our coffees. So to cut the roast, Ilvana opens the door to the roaster.
205 degrees, 10 minutes roast.
And we come tumbling out of this hot spinning oven into a cold cooling tray, where cold air is sucked through and we rapidly cool down to room temperature. All the reactions, all this movement and these reactions around us, they all get slower and slower. And let's get out of this bean, because if we hang around too long, we might get crushed in a coffee grinder. We turn our spaceship around and zoom out. And out the back window, we see what was once a plant cell. Tall, thick mountains encircling a castle in a city with a giant lake. But now it's all brown, with holes everywhere, like the surface of the moon. And in and amongst all these craters are aroma compounds that will smell amazing to us. Flavors that just weren't there before. And guys, I have that feeling you get when you're on the plane coming home from a vacation, where you're just kind of staring out the window, reflecting on everything that just happened. This roasted coffee bean used to be a green coffee seed. This was a backpack full of food that a mother plant gave its little embryo to eat. What a beautiful gesture of love. But what we see out the window here is all that baby plant food has been reacted, transformed into gorgeous aromas that we humans love. And of course, this is not what the mother plant intended when it lovingly packed this backpack full of food for its little kid. But this baby plant food that has been transformed into flavors, those flavors are what make us love coffee. It's the reason so many of us love working in coffee. It's probably the reason you're listening to this podcast, because you love coffee so much. Maybe it's kind of corny, but I think it's a beautiful thing that the love that this mother plant gave its seed has now been transferred to us to create our love for coffee. Okay, we've returned back to normal size. Exit on the left. Mind the gap. So guys, thanks so much for joining me on this journey. I know it feels like we covered a lot, but really, my earlier drafts of this episode covered so many other things that in the end I just decided not to include because it was kind of too much for one listening session. But don't worry, because I'll create some Instagram infographics that explain this stuff. So follow me on Instagram at Filter Stories Podcast, link in the show notes. Now, in the next episode, we are staying with coffee roasting, and I take you on a historical journey into how coffee roasters got bigger and bigger, and how we managed to roast faster and faster and faster. We are looking at how coffee beans take on heat. And I ask the question, why do we take so long to roast coffee? Especially coffee roasters could be roasting their coffees much, much faster if they didn't use drum roasters. Are there other roasters we should be using instead? So press the subscribe button in your podcast player right now so you can hear that episode as soon as it drops. Oh, guys. This episode, I hope you enjoyed it. I really do. Because this one took forever. The entire series, The Science of Coffee, it's made entirely by me, including writing the piano music, and in this case, also finding all those crazy, amazing special effects sounds, and so much technical stuff. I was bashing my head against the wall for so long. And if this episode helped you understand coffee, biology, flavors, whatever, it would mean so much to me if you would share it on Instagram as a story, do a screen grab and tag me at Filter Stories Podcast so I can thank you, or share it on your coffee Facebook group, or post about it on Reddit, my personal favorite social media platform. It would mean so much to me if I could see others also enjoying and benefiting from all this research that I've done. And speaking of research, look, there are two massive thanks I want to give in this episode. People who really took so much time out of their busy schedules to help me. The first is Sebastian Opitz of the Coffee Excellence Center. He is an excellent educator, communicator, and if you want to go deeper into coffee science, I strongly recommend you sign up to do the Certificate in Coffee Excellence that Sebastian helps teach at the Coffee Excellence Center. Link in the show notes. And the other massive thanks goes to Anya Ran, who was so generous with her time and is also a wonderful educator, and in fact has written a book on the Maillard reaction and many other wonderful things. Link in the show notes. Now, what else is in the series? In the next batch of episodes, we go to Brazil to discover how coffee farms find buyers, including directly trading with roasters using Algrano, a direct trade platform. And then we're in the mountains of Colombia, tracing the difference between specialty and commodity supply chains. And I look at what coffee exporter The Coffee Quest does in Colombia to try to preserve and sometimes even improve flavors as they make their way down from the mountain slopes to the port. I am then on a philosophical journey looking to understand what even is specialty coffee? How do we define it? A journey supported by the water filtration manufacturer BWT. And in the episodes before this, I go deep into extraction science, looking at how to make delicious cold brew using the cold brewing kit made by Toddy. Thanks again for listening, and I'll see you in the next episode.